Our next speaker is Magnus Danielsson. He's worked with large-scale transport and network switching, network synchronization, and GPS-independent time transfer systems for 22 years. And I gotta say, that sentence and not messing it up was hard. Designing the Net Insight time transfer system, oh, there I did, I messed up. He has also research in time and frequency, part of the JTPC for IFCS and EFTF, 2019 and 2020. He's the technical editor for the upcoming IEEE standard 1139 revision, maintainer of Stable 32. He also works on GPS GNSS robustness issues, including bugs, effects of jamming, and has presented before at the USPNT Advisory Board. Magnus Danielsson is a IEEE senior member, and he comes to us from Net Insight. Magnus.
Thank you. So today I want to discuss how we can use the IP network-based to distribute the timing, the UTC time that we then use for ATSC single frequency networks. So first of all, for those who don't know how the single frequency networks works, in order to support multiple transmitters in the same domain on the same frequency, we need to transmit the same signal at the same time. And since the receivers are able to handle the situation that you have a signal from a transmitter and a multipath reflects from a building or a lake or whatever, they already have the ability to handle delays, delayed versions of the signal. And with this, we now have the tolerance of the receiver. So the receiver is not able to distinguish this from the scenario that you actually have multiple receivers sending the same symbols at the same time, more or less, and on the same frequency. So they will now support each other in a constructive interference. And this is a wonderful thing because you can drop transmitters now in ways to fill in without requiring additional frequencies. So this is a good thing. To do that, we need good timing. If we're not doing the multi-frequency network, we only need to make sure that the transmitters are within the necessary specs for transmission on the frequency. We don't really care about timing. It becomes when it becomes. But here we all of a sudden, to do this, we need to make the timing good. So therefore, in the ATSC 3 specs, the system time is described to be using that of UTC and time. So this is the core thing. The reason we go about this is, for some reason, we have GPS. GPS provides us with a timing service which is sufficiently good for this application. It should give us within ±1 microsecond if we look on the spec. Actually, it's performing much better. So this enables this technology. So it gives us a distribution of time over a large area for a relatively cheap price. And that's wonderful because it allows us to do this. We can compensate for the delays through the network, and we can then make the receivers, the transmitters actually work on the same frequency in a coherent way because they're really timed and they have the same symbols at the same time. Now, the trouble with GPS, and this is just one example of many to scare you. Whoa. So, US Department of Homeland Security, they have concluded that we are very dependent on GPS. And there is a number of incidents, for instance, a 2013 event that shut down or partly shut down the Newark airport because somebody wanted to jam the tracking system of the truck as he was driving home to eat lunch at home. Another event was the 2016 event where the GPS system actually malfunctioned in an interesting way. That caused big pain for many transmitters and other telecom operators. And we had, this year in July, we had a Galileo GNSS outage. Galileo is the European version. So, I mean, in this context, we talk about GNSS rather than GPS because we have multiple systems. It's good to use them because they provide some redundancy, but it doesn't help all the cases because you can jam them and set things up. So, and this is to illustrate how they're raising awareness about how sensitive systems have become to this issue. And we see some countries actually have legal requirements. I expect to see more countries to have that. And so I'm bringing it to your attention. Luckily, there are ways to handle this. So one proposal that you could do is you could use PTP, for instance. This sounds wonderful. It's a technology that is there. You can use it to distribute things, but you need to use a fully timing supporting infrastructure. So your switches, your routers, they need to support SyncKey, they need to support PTP. You need to engineer it strictly hop by hop, make sure that all the path works, and you might need additional timing sources. The limitation lies in the FTC part, fully timing support. Because if you're renting capacity, today we do that when a lot in the telecom world, we rent capacity from somebody else to get where we need to. How do you get assurance that part of the network has the full timing support? PTP network can also, they can be attacked in various ways. And we have heard that over the days already. And there is also a number of other issues that comes in. If you're not having good support, variable traffic will eat your position as well. So the trouble with this is it's hard to engineer and control so that you ensure the integrity of your network. And this is just one of many cases where people have been looking at PTP and the problems with PTP, how you can actually attack it, etc. This one was by IBM and Marist College, and they were able to, with a very short attack, create a huge difference. Now, there are ways to handle this, of course, but it needs another type of engineering. And also, remember, if you're now going over somebody else's network, how do you know that that will not create scenarios, either by intention or unintentional, setting off your timing? So it's a little bit tricky. So the thing that we have done is we developed for the DVB-T market something called time transfer. And we have been operating that for 12 years now, so this is one we did earlier. And we have adapted that to work over IP networks. And in overall, we kind of look on the whole system. We try to have a holistic view of how time is transported. And in essence, we need to think about that we need to achieve typically plus or minus 1 microsecond. You can actually allow for more in many times, but we have seen and run over networks long distance with a lot of different hops, 170 nano. So that's just one example from the heap. An important aspect is that we can also use the meshing network. Typically, you build a rather complex network, and for the core part, you will have multiple paths. And these are really good because we can provide self-healing if there is a break or something. We can also use it for diagnostics. We can build that on standard business VPN. We used the AF42 class, for instance, in the test case that you will soon see. And we then transport the STL data through it as well. And we have different ways of doing that. Now, so there's 2 ways to do this. The first one, you can use our boxes to kind of just build an overlay network to help you with the timing, and you use the existing data path for the STL itself. But the alternative is, we come from a tradition of building transport equipment, so you could actually use our boxes to also handle the STL streams directly and to be a more integrated solution. And that has benefits because you see both the timing and the transport of the signal to the transmitters. This is what we already done in multiple countries, so this is the one I'm comfortable with. Now, this is the thing that we have done in real time. This was, we did a case in a country where we were running over their core MPLS DVDM network. And we just had the AF42 level off, so we didn't have the premium class, the platinum transport. And after calibrations, because you always have asymmetries, we were able to keep this within 170 nanoseconds. And this is in a situation where we now are independent of GPS GNSS. And we have used this in multiple countries, and we even had GPS incidents, and those countries have not been affected in their operational concerns, in their operations of this. So it just keep on coasting on and working. So, and this is important because you need to feel that you can keep your network operating even if you have a scenario. GPS is a fine service, but you need an alternative path, alternative way of handling things. So this case, it was over a 2,000 node core network, and we just used a setup. Typical, you will see the overall having multiple hundreds of nodes hooked together to create a mesh that then distributed out to the transmitter sites. When we did this, we just used the basic IP service. So there was no border clocks or there were transparent clocks, so there were the full timing support or partial timing support. So no support really from the network, it just sat there. And this is important because that avoids the whole forklift upgrade of that network. And we avoided a lot of the engineering in that network. And this also allows you to run over the rented capacity because you have really the same situation. When you can engineer things in your core network, that's fine. But it's good that you have a way to go over that and into the parts where you don't have as well engineered situation. This was also a full, when we did this measurement, this was running on a full network. So this was not a silent network at all. We did see a lot of interference, but we were able to suppress it and keep it away from the transport. And this is just one scenario jump here. And this is just to illustrate what we can do today. And it helps us to make these networks robust and resilient to the various problems you can have with GPS, GNSS, and keep operating. So that's it. I made a very short presentation today, but that leaves a lot of room for questions.
So can we have questions from the audience? Some timely questions. I'm going to keep doing time jokes all along because I just love this topic.
What?
I'm going to keep doing time jokes. If we can have some timely questions from the audience, perhaps.
Yeah, well, that's a timely question, though.
Merrill Weiss Group, and I'll mention chair of the ATSC 3 committee on STL and SFNs that wrote the A324 standard that defines how the SFNs work in ATSC 3. So one of the requirements that we had in putting together the STL document for ATSC 3 was operation over unidirectional STLs. Do I understand correctly that the technique you're describing requires bidirectional connectivity of a data network?
Well, for the timing transport, we do bidirectionality for the timing transport, but we don't require bidirectionality for the STL signal set itself. But for timing, you need the bidirectionality.
So a one-way microwave path to a remote mountaintop site would not carry that?
No, because regardless of which time of timing transport you'd use, you need the bidirectionality to measure the timing distance. So if you call that NTP, if you call it PTP, or what we are doing, it has the same requirement. Because we need to send a message here, a message here. We can use those to measure the distance, compensate for it, and then provide. That's the core of any time transfer, two-way time transfer mechanism. There are ones that you could send one message down the line, but then you need to go and calibrate that to calibrate that delay. Now you're very dependent on the stability of that delay. And so that needs to be transported in a way that is extremely solid in timing. Otherwise, you will move around. Whereas if you're doing two-way, you can continuously track and compensate.
Or alternatively, you can use at the site a signal that you can receive not over the STL, but also with the unidirectional transmission, such as GNSS.
Well, you can use GNSS, but then you become dependent on that for your constant operation.
Understood.
And this is really one of the concerns coming up. If you are now in a situation where you do not want to have your 100% time, operational time, dependent on that GNSS receiver to operate, then you need to look for alternatives. And alternatives will eventually have you look on the network. And then the trouble is, if you just try to use P2P, for instance, and use it in an environment where you cannot do the full timing support, then you are in a trouble. So you then go from trying to solve something into a new problem. And we try to kind of show that there's alternative approaches to address those. So you can have a network-based timing for those scenarios that is more robust. So that's what the proposition is.
Yeah. Understood that it's an alternative. So at some location, there must be a highly reliable source of time information.
Yes.
At the start of your network. What is that source and how is it delivered to that location?
You could choose multiple approaches to that. So one approach is you can just use a GPS GNSS receiver. You can make sure that it has a little bit of extra holdover. And you can decide how much holdover you want in that position. Now, an alternative is that we don't really require it to be on one spot. We have no problem of having it distributed over the network so that if say one or two sites have an issue, we can actually take the timing from another place and distribute it to all the locations. And we have ways to handle that and reroute the full network quickly to converge to the timing source. This way, if you have an effect, if you have a failure for whatever reason on site A, site B and site C might handle it. And if site B is also having problems, well, site C can feed the whole network. You can also divide the network up and feed different parts, because if there would be an issue, convergence time for that part would be smaller, as well as you would be able to have smaller parts of the network affected by the problem at all. So there are many different ways of solving this.
So your sites A, B, and C would be the sites where you're bringing the precise time information into the network, is that correct?
Yeah, so you can choose yourself suitable locations in your network where you feed timing in. And you can choose either of the different approaches to take that time and distribute it into the network.
But again, it requires a two-way or a bidirectional network.
That is, if you want to do network-based timing, you need to think about two-way, regardless of, that is just the nature of how it works. And
I guess the point that I'm getting at is that there are some locations where that can work, and there's some locations where that sort of network connectivity is uneconomical. And so I'm trying to separate
sure.
the sorts of instances where this might be useful and where it would not. So how much difference is there in the reliability of using, that comes from using a bidirectional network as opposed to using multiple GNSS signal sources that are on different systems like GPS and Galileo and so on?
It depends so much on the operational situation for the GNSS GPS receivers. For one customer, for instance, they were having a situation where they were running GPS receivers, but they are in Norway. They have winter. So they had once a week, on average, spikes of ice were falling from their transmission tower and crushing the GPS antenna. Mm-hmm. And that is just to illustrate one of several ways where your antenna, your cabling, and your receiver itself can be part of the problem. It doesn't really care if that is happening or if somebody goes out with a jammer to hit specifically you. It's the operational consequences of that which is becoming an issue. And how much you like to tour the country to fix your receivers. And so they were in a pain until they enabled this. And now they can be much more relaxed. If one receiver fails that is feeding the network, they can relax because they can then just scheduling it in with other service because they can feed it from a different path. And this changes the whole operational concern aspect.
Okay, understood. Been there, done that with antennas and ice. So what I didn't see in your presentation, and maybe I missed it, is an actual description of how this works, other than it's a network and it's better than PTP in terms of the stability of what you deliver. Can you describe what's inside your magic box?
Well, to be honest, I didn't make the slides. But I can tell you, we are sending IP packets with standard IP UDP packets. We put timestamps on them, and we put timestamp back when it comes, recover timing, recover it. If you look in the paper that comes with this presentation, it will give you more details. So that's the one I wrote. So, we're essentially just sending normal traffic through and recovering timing, doing the things that needs to be done, then have an aggregated routing of synchronization that then solves many of the routing issues and ensuring that things work. So it's similar to what PTP does, but it does it in a very different way because we needed to do it in a different way. And this is why we come up with a slightly different solution. You will recognize yourself, but it's different.
Yeah, I will remind everybody that each of these presentations comes back with a paper that is going to be published, and with a lot of tremendous detail that you couldn't just fit on the slides. And so it's always a good thing to follow up if you're interested in that with the paper, because as one of the editors of those papers, I can say you did a great job and a lot of detail in there. So
let me give you one other just pointer on the ATSC 3 STL system. It's TAI, not UTC at that level.
Thank you. We have a couple minutes. There's a couple questions I have. So one of the challenges whenever we put anything on the network is that there's also people that like to cause grief on the network, whether by accident or in some cases deliberate grief. Have you guys considered how to respond or how to authenticate or how to protect this signaling against deliberate tampering or people trying to cause disruptions for whatever reason?
what we have seen mostly is acts of life. And what we're trying to protect is really the acts of life thing. I mean, we have seen people do really stupid things, including putting a Christmas tree on top of the GPS antenna. So, I mean, in practice, it's easy to come up with all the things you can scare, GPS jammers and stuff. But in practice, most of the things that we've seen in all the installations, it's been accidents and people.
So you haven't specifically worried, because I'm professionally paranoid, and I always look at any traffic on the network and say, what happens if somebody's deliberately falsifying this traffic, and how do I deal or address with that? Is that something you guys have considered yet, or is that sort of you haven't hit it yet, so you haven't worried about it?
You need to keep the mic up right here.
The question was, I'm a professional paranoid for work,
yeah.
And I always worry about people that deliberately insert stuff onto the networks to deliberately cause disruption,
yeah,
and shutdowns. Have you considered countermeasures or mechanisms in your workflows to guard against that and respond to it?
Yes, I mean we have basic methods to first of all we suppress a lot of the noise from the network itself. That in itself actually do a lot to suppress even intentional threats. We have then ways to monitor and overview the whole thing. So we are tracking how the timing of the different parts of the network are moving around. So, and that's kind of part of the whole thing that we kind of want to keep tab on how things go. We monitor each link very carefully. We have good statistics. And we get warning signs from all different parts, and that gives us a good indication of where, if somebody is messing with us. So, I don't care if it's intentional or not. I just care about the operational consequences.
But you can see and respond, so you know what's going on. And speaking of operations, I mean, this is deployed, right? I mean, how many places is it deployed in today in use? We
have 15 plus countries operating this for their national networks. So this is, I mean, I don't know how many transmitters we're feeding, but it's a few thousand.
So it's not just theory, it's real life.
Yes, it's practice. So,
okay.
And this is like the oldest network's been operational for 12 years now. That's some 800 nodes. And depending on the country and the topology of the country, the number of nodes vary. But I mean, we have a variety of different topologies and requirements. So I mean, it's seen some real life.
Okay. Well, thank you, Magnus. Thank you very much. Can I a round of applause for our speaker, please?